Okay, we're going to go ahead and take a look at the cross multiplication theorem. And let's go ahead and review the equivalent fraction theorem. And I'll get my pen here. But basically, and again, this is very abbreviated because we haven't quantified our symbols, but we all agree that these have to be whole numbers. So given m over n, or the fraction symbol for m over n and k over l, if there is a constant, or if k is equal to some constant times m, and l is equal to a constant times n, then we can say m over n is equal to k over l. Well, let's take a look at that. Since that is a valid statement logically, let's go ahead and check it to see if it works backwards or if we turn it around. So if you notice, we have this statement being stated first. So if m over n equals k over l, then is it true that k is equal to c times m and l is equal to c times n for some non-zero whole number constant c? So let's take a look at an example. Let's do 6/9 is equal to 16/24. All right. So this is a true statement because they both equal 2/3. So both of these do occupy the same point on the number line because if you find an equivalent fraction, 6/9 is 2/3 and so is 16/24. But the problem is here that there is not a constant. So here's our but. There is no number, so 6 times, and I'll use c, is equal to 16. There is no whole number that you can multiply 6 by to get 16. And the same thing with 9. There is no whole number that you can multiply 9 by to get 24. So there are no whole numbers that are going to satisfy this. No whole numbers available. Okay? But we agree that they are equivalent. So is it true that we can find if we can't do this, then how can we determine that these two fractions are equivalent? Is there a way to use m, n, l, and k to prove that they are equal? Yes, there actually is. And what we do is it's called the cross multiplication theorem. So go ahead and pause the video so you can write this down. Given two fractions, and again, we're already assuming, because we've been doing this for a while, we're not going to keep stating that m, n, k, and l are whole numbers. That's what we've been using, so we're just going to know that that's what we're talking about. If m over n is equal to k over l, then m times l is equal to n times k. So let's take a look at our example again. 6/9. Oops. Go ahead and do example. Let me erase that. And since my writing is over that, let's fix. Okay, so if we have 6/9 and it is equal to 16/24, then what we can do is, by using the fundamental fact of fraction pairs, if you're not sure what that is, again, pause the video, go look it up. But basically what we can do is there's any two fractions that we can make equal by having the same denominators. And the way we're going to do that is if you take 6/9 and our constant is going to become 24. Now where did I get 24 from? Well, if you notice, it's the partition of the second fraction. So if we do that and we take the second fraction, 16/24, and we're going to use 9. Now notice where I get 9 from. We're going to use 9 as our constant. Notice what happens to our denominators now. I'm just going to circle it. Without actually multiplying these out, what can you say about these two denominators? Well, hopefully you said that they are the same, because 9 times 24 is the same as 24 times 9. Okay, so what you end up with is, if you multiplied these out, this would be these copies, 6 times 24 copies would be 144, and 9 times 24 partitions would be 216. And if you did the same thing here, this would be 144, and this would be 216. So basically, here's the proof that both of these are equivalent, and therefore the thing is, the numerators being the copies, the number of copies of partitions, are equal. So here's the proof. Suppose that we take any fraction, m over n, and it is equal to another, not another fraction, but another fraction symbol, which is k over l, using the FFFP, we're going to rewrite m over n equals k over l. Remember, we can write this with the same denominator, and in order to do that, we have to write it by multiplying it by a constant. So this is going to be m over n. Our constant is going to be L. And we're going to say that that is the same as k over L. And the constant we're going to multiply is n. So k times n and L times n. Even though these are written backwards, remember, by the commutative property of multiplication, they are still the same thing. So what happens to these is, if we keep going down, remember, this is ml times 1 over nl. Remember, it's multiples of partitions, or copies of partitions. So that's the definition of a fraction. And this is the same thing. So k over n times 1 over, and I'm going to switch it around, nl. I just switched these around. But if that's the case, these would cancel out, and what you're left with is m over l equals k over n. All right? So if I go back, that's what we have right here. So going back to our, if you look back at our definition, here is what we just ended up with. So m times l equals n times k. And there it is. So there is our proof that it works. We can prove it symbolically by using, remember, we used FFFP to rewrite this. And then the definition of a fraction means that it's the numerator times the number of copies, or the number of partitions. So here's your copies, here's your partitions, and we can, because they're multiplying by the same thing, we can get rid of those that cancel out, and you're left with just the copies. Copies equals copies. All right, let's take a look at that backwards. Suppose we start with m times l and n times k. Well, if we write this as, I'm going to go ahead and write this, and then what I want you to do is tell me, or write down, what is the proof. So let's start with m times l equals n times k. I'm going to write m over n. Okay, and I'm going to multiply it by the constant of L. I'm going to take this, and I'm going to write n times k over n times L. Remember, these are the same because I'm not going to give it away. I want you to write next to it. So write next to this, what allows me to do this? What rule or law or theorem allows me to write this? I'm going to see if you can figure it out. From there, I'm just going to rewrite this because I'm going to show you what's going to happen, and this will be another rule or law. So I'm just going to copy this down again. All right, notice what's the same here. Well, I can cross these out because they are the same, and I can cross these out because n over n is the same. What did I just do there? Go ahead and fill in that blank. So what does that leave me with? M over n equals k over L, and we're back to where we started from. All right, did you figure out what these are? Well, this would be the equivalent fraction theorem. I'm just going to abbreviate it. So equivalent fraction theorem allows me to do this step right here. And what did I end up doing here? Well, basically the cancellation law. So that is how we do proofs. You just did your first proof. We use definitions, theorems, and laws to help us get from one point, in this case m times L equals n times k, to our starting point from our previous argument, which is m over n equals k over L. But every step has to be a proven law or theorem. All right, so let's try that with this. Explain why 6 over 8 is equal to 9/12 using the cross multiplication theorem. Go ahead and stop the video, work this out. Again, as you do the steps, you're using numbers, but go ahead and put the law or theorem as to how you're doing your steps. And then go ahead and start the video, and I'll show you the answers. Okay, so if you've got this figured out, this is what you should have. By the fundamental fact of fraction pairs, you can multiply 6 over 8 times 12. So we're going to use 12 from our 9/12 as our constant. And the 9 over 12, we're going to multiply by a constant of 8, which came from our denominator of the other fraction. And when you multiply those out, you get 72 over 96 equals 72 over 96. So the same result can be achieved if you just multiplied 6 times 12 and 8 times 9. And if you notice, that's why they call it cross multiplying. Here's the 6 times 12, and here's the 8 times 9. So instead of now, if you learned how to do this, you didn't have a reason why. This is the reason why. Because when you use the cross multiplication theorem, it forces our denominators to be the same. And since they're the same, we don't even really have to look at them. We just need to look at the numerators to see if they are the same. All right, we'll practice this more in class.